H3O plus, for example, we're going to start by, like I said, determining, if you look at the first rule here, determine the total number of valence electrons in all the atoms of the molecule. So we're going to look for all the valence electrons in this molecule, and then we're going to add or subtract those extra electrons that we need to, that's associated with the charge. So in this case here, same as last day, we're not talking about bonding capacity, so that's the only thing here. We're not saying that, you know, we're not talking about bonding capacity, we're talking about valence electrons. So I'm going to actually just insert one here. If we do an H3O plus, each hydrogen has how many valence electrons? 1, okay? We have 3 hydrogens, so that's a total of 3, yes? Okay. Oxygen. How many valence electrons does oxygen have? 6, right? So we're going to put in there 6. So that's how many valence electrons we have so far to work with. The +1 indicates what? That we've gained electrons or lost electrons? Gained or lost? Plus. Lost, yes? So we've lost 1 electron. So we're going to take 1 away. Okay? So normally, if we're doing H3O, we'd have 9 valence electrons available to us. This one is given 1 off. So we have, in fact, only in this case, 8 valence electrons to worry about. Okay? 8 valence electrons. You should write that number down somewhere. You should probably do that math. I would go through these exact steps. That way, we know exactly how many electrons we have to deal with. Step 2 here says, choose the atom with the most unpaired electrons as a central atom. In other words, choose the atom with the best bonding capacity or the most bonding capacity. When you look at hydrogen and oxygen, which one has the best bonding capacity or the most bonding capacity? Oxygen, yes, has a bonding capacity of 2, yes? Okay, 2 unpaired electron. So we would say, okay, I want oxygen to be my middle one. Step 3 says here on the first page, draw a skeleton structure for the molecule by placing other atoms around the central atom. So we're going to use that as our center. We're going to put the other ones, we're going to draw what we call a skeleton structure. So we're just going to put the other H's around there. Now, you might say, well, how do I know to put them there? Well, it kind of goes back to that thing we had just talked about earlier, right? Most things have 4 things around them. That's quite a common structure, okay? And if they don't, we'll adjust it later. It's not a biggie, all right? We can fix that. So, we start with this here, okay? That's step 3. Step 4 says the following. Draw 1 pair of electrons between each pair of atoms to represent a single bond. Draw 1 pair of electrons between each atom to represent a single bond. Do we have a molecule here yet? And the answer is no. We need to connect them together. So, hydrogen can only form 1 bond, 1 bond, 1 bond, yes? Now I'm putting dots there. Can you put a line there instead? Sure you can.
We're going to start on grade 12.
Sure, you can put a line there if you want to. Okay, I'm going to use dots right now, and at the end I'll put the line in if you want me to. But usually when you do these, you see dots. All right, usually it's not the lines, but you can see lines as well, covalent bonds. So, how many electrons did I use so far? 1, 2, 3, 4, 5, 6, yes? So I've used 6 electrons to fill in that, basically those bonds between the atoms. Then it says here, so I did that. That was step 4 here. If you flip over the page on that, to the second page, it says, place lone pairs of electrons around all the atoms except the central atom to form an octet. Sorry, that's this one here. I did that, okay? Well, okay, I put the bonds in there. And then they're saying, go back and fill up the octet around the outside atoms first, is what the rules say. So if I looked right here, for example, do I have to put any more electrons around there to fill up the octet for hydrogen? Hydrogen only needs 2, yes? So I'm actually done in this case. So I don't have to worry about that. So, good. Okay, did that. And then it says here, If all the valence electrons in step 1 have not been accounted for, you can add one or more lone pairs to the central atom. So I've used 6, I can use 8, right? I have 8 to use. I've used 6, so I can put my 7, 8 on my central atom now. Okay? In other words, I've filled up the outside atoms first. And once again, more examples will show you what I'm talking about. I filled up the outside ones first, and now, okay, I fill up the middle one, if I can. We put brackets around this because it is an ion, just like we did the other day, don't forget. And we put a plus sign in here showing that I've lost actually 1 electron. Because remember, if we draw H3O, we technically have 9 valence electrons. I didn't draw H3O, because if I did, I'd have to have 9 valence electrons. That doesn't make sense. So where did that extra electron go? Well, it's gone somewhere, probably to a nonmetal. Okay, so it's probably another nonmetal that I haven't drawn up here, and I didn't draw. It's maybe chloride, for example, took that extra electron. I don't know. Maybe it was bromide. Maybe it was nitrate. I don't know. Okay, but that's what you would do for that one there, H3O+. This is also, by the way, I'm just going to tell you this right now. This is called the hydronium ion. Hydronium ions, what does that look like to you? Pretty close, except for something one letter different. What does that look like to you? Looks pretty close to what? Huh? Water. Is that what you said? Water. H2O, right? H2O with an H plus added onto it. Where did that H plus come from? Well, we'll talk about that in Unit 3. This is actually what we're going to measure. This is an acid. H3O plus hydronium ions are acids. All right? So we're going to talk about that in Unit 3. All right? So just so you know, that won't be the last time you see that one for sure, hydronium ion. Next, we had to do, I forget, SO4 2 minus? Yes, SO4 2 minus. So, same thing, okay? You start by adding up valence electrons, step 1. Add up all the valence electrons and account for the charge. This one has, sulfur has 6 valence electrons. Each oxygen has 6. So 6 times 4, because we got 4 of them, is 24. And this one in particular, sulfate, has gained a 2 minus, right? Has gained 2 electrons. So I want to add those 2 electrons onto here, okay? Because SO4 has taken in 2 electrons. That's what the 2 minus means. So I have 2 extra electrons I can get to use here. That's a total of 32, okay? Like I said, more examples will show you the different options that you have here, okay? So we look at sulfur, we look at oxygen. That's step 1. Step 2 says, right here, choose the atom with the most unpaired electrons as a central atom. Which one has the most unpaired electrons, sulfur or oxygen? Most unpaired. Sure, Stephen. I don't know, is it? They are the same, right? That's a trick question. Sulfur has 6 electrons, yes. Oxygen has 6, yes. So they both have 2 unpaired electrons, true. So, does it matter which one we pick? And the answer is yes, kind of. We want to keep it symmetrical, right? We want to choose, usually in most cases, the atom that's by itself as the middle one. That way we can kind of keep it symmetrical. If we pick O as the middle one, it's not going to look the same all the way around. So usually we pick S for the middle one here, in this case. O, 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 and O. A lot of O's there. O, O. So usually we want to do it like that, okay? By the way, I kind of skipped a little bit there. So once again, step 1 was add up the valence electrons, account for the charge as well. Step 2, choose the atom with the most unpaired electrons, put that in the middle, that's their central atom. I chose sulfur because it's the only one by itself. They both have 6, so it doesn't really matter. Choose the one by itself, put that in the middle. Draw a skeleton structure, check. Draw 1 pair of electrons between each one. So I have to make this into a molecule. To do that, I got to go 1, 2, 3, 4, 5, 6, 7, 8. Yes? I have to hook that together. Otherwise, I don't have SO4 as a molecule. I have a bunch of sulfurs and oxygens. That's step 4 there, basically. Draw one pair of electrons between each pair of atoms. Next page says the following. Place lone pairs of electrons around all the atoms except the central atom. Hydrogen, of course, can only have 2. So basically what they're saying is, at this point, after you hook them up, this is kind of what my version of this is, after you hook all these elements up here, you then go to the outside and make sure they have an octet first. So you go to the outside atoms, make sure they have an octet. So we used 8, right? Here's 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And I can count to 32. Okay? Yay for me. So, I've used, 32 electrons. You make connections in the middle, hooking all the atoms together. Then you go to the outside. Make sure they have an octet. Then, if you read the instructions here, if all the valence electrons determined in step 1 have not been accounted for, you can add one or more lone pairs to the central atom. We don't have to do that. We've accounted for all the electrons, right? I told you we had 32, right, to use. Have I used all 32? Does everything have an octet? Does everything have 8? So, you know what? I'm pretty sure we're probably good. We're probably done. All right? In fact, we are. Don't forget the brackets with the charge, though, to indicate that in this particular example, we've gained 2 electrons. Okay? So if you use them all up and everything's good, everything's got 8, we're done. Okay? Fine. Is that always going to work? Do they always work out so nicely? Do they always work out like this? Absolutely not. Okay? So when we take a look at the next one here, NO3 minus, okay, we're going to do actually probably another 3 examples, including this one. So we got another 2 after this one here. Nitrogen has 5. Right? This one has 6 for each one. Valence electrons we're talking about, not bonding capacity, valence electrons. So that's a total of 18, right? 6 valence electrons for oxygen, because we're showing you all the valence electrons. And of course, don't forget your charge, and 1 in this case. This one has gained 1 electron. That's a total of 24. 24. Step 1. That is step 1, right? Add up all the valence electrons. Did that. Step 2. Find the one that has the most unpaired electrons, or the one that has the highest bonding capacity. Put that one in the middle. So in this case, nitrogen. Usually, it's the one by itself. Okay? Nitrogen. Draw a skeleton structure. Oxygen, oxygen, oxygen. Okay? Once again, you might say, well, why put them there? Well, usually, there's 4 positions around an atom, usually, except for hydrogen. And if you know what, if we don't need all 4 positions, we'll fix it later. It's fine. Okay? The next step says we need to make a molecule out of this. So always, 1, 2, 3, 4, 5, 6. Okay? Hook them up. Right? Those dots represent covalent bonds sharing of electrons. Remind me at the end, please. I will show you. Okay, well, I'll draw them with the lines if that makes you happier today. Okay, there's 6. Where do the next? So I've used 6 out of the 24. Where do the next ones go? To the outside first. Outside atoms always have to fill their octets first. So you might be tempted to put them up above the nitrogen here. Do not do that. Okay? You do this part first, you make a molecule, then you go to the outside. Don't worry about that. So that's 6, 7, 8, 9, 10, 11, 12. I got 8 around oxygen. Okay? So octet. What did I say? 12, 13, 14, 15, 16, 17, 18. I have 8 there. 19, 20, 21, 22, 23, 24. I have 8 around that oxygen. Okay? Good so far. Okay? So make a molecule, go to the outside first. Now, we stop and we say, okay, I've used all my 24. I've used all my 24. 8, 8, and 8, 24. Oxygens are all good. Am I good? Can I stop? No, because what's the problem here? What is the problem? Simon. Yeah, so we got to fix it somehow, okay? And this is where I was very careful before, okay, to use the term usually before. And I said, usually this is the case. Usually this happens, usually. If we go back to the rules here, okay, now we're kind of on the last one here. It says, place lone pairs of electrons all around the atoms except the central atom to form an octet of electrons. Hydrogen, of course, only needs 2. If all the valence electrons determined in step 1 have not been accounted for, you can add 1 or more lone pairs to the central atom. So the key word there is, if you haven't used all the electrons, if you haven't used all 24, you can put lone pairs on the central atom. But we have used all of those 24, yes? This is all we have. Okay, 24, that's it. So the next one underneath there says the following. If you don't have an octet, you are allowed to move lone pairs until you can fulfill that octet. So you can put in 1 lone pair, move 2 lone, sorry, I shouldn't say put in. You can move 1 lone pair. You could move 2 lone pairs. You may even have to move 3 lone pairs somewhere to help you out. So what does that look like? Well, I said usually lone pairs are not involved in the bonding process. Usually. Here is where you get a chance to see where they are. Because ultimately, lone pairs are still valence electrons orbiting these atoms. Okay? So you can pick whichever ones you want. I don't care. I like these ones right here. I'm going to move those into there. So I'm going to move those 2 electrons into there. And what's going to happen here, I'll keep it the same here just so you guys can see. We get that over there. I'm going to keep these, obviously. I haven't moved anything here. Oops. Well, I should move those over a bit. There we go. Okay? So, now, and this is kind of messy here too. Give me a sec here. There, okay? So I moved the lone pair in. And now, just by simply moving that 1 lone pair in, you can actually see that we've actually fixed it now, right? Look, 8, 8, still got 8, yes? Because they're still being shared there. And then, still got 8 there. Okay, now, anyway. So that's how we can fix it. And you might say, you're just making stuff up. Well, no, I'm not. Okay, valence electrons are orbiting. So if they have that ability to be shared, if they want to become more stable, that's how they're going to do it. Okay, that's a possibility. And once again, as always, you might say, I don't want to pick those lone pair, right? Bucking the system. Not even paying attention, right? Hey, just eating their whatever there. I don't know what that is. In a cup? Your mommy's nice. You know what my wife made me? I shouldn't, just a minute here, let me turn this off. Anyway, okay, getting back to chemistry here. She doesn't listen, just in case you think that's the case. Well, actually, if you have Apple TV, you can go onto YouTube, and I've done this once, and you can actually watch it on TV, on a big screen. You know that? I have Apple TV. I'm not bragging or anything, I'm just saying. All right, anyway, I'm pretty techno, if you, yeah. Do you have to move that pair? Absolutely not. You can move any pair you want. I don't care. But you have to come up with that octet, right? So we'll talk a little bit about that in a sec. Now, is this the best diagram? And this is what everybody wants to know. Is that okay? Sure, that's fine. You leave it like that for right now. It's no biggie, okay? Technically, though, how many things did I end up with around nitrogen? I only ended up with 3, yes? So is that really the best diagram? Like I said, we've talked about this before. Everything wants to spread out as far apart as possible. So is this the best diagram? Probably not. Oh, by the way, don't forget, right? And that. Okay? Is that the best diagram? You'll soon learn that no, it's not. Usually, I better give myself a little more room here, right? So we have a double bond here. See how everything kind of spreads apart a little bit more? Electron pairs are in angles. Okay? It's not the end of the world, I'm just saying. And then we would do something like this here. And since there's only three things or three bonds around that, that's how we'd represent that one. Okay? That's probably your best diagram there. All right? Now, something else can happen with that. We'll talk about that a little later as well. I think we've got time today. So that's NO3, okay, minus. Next one was CO3 2 minus, right? I believe, carbonate. So real quick here, because I want to get to the next one. There's one more I'm going to do with you here. There's 18 there, yes. We're talking about valence electrons once again. So for those of you that were kind of had pictures or whatever, 4 for carbon, 6 for each oxygen, valence electrons. Don't forget the 2 minus. We need to add on 2 more here. So that's what, 24. I just had to get the calculator for that one. Put, once again, most unpaired electrons, central atom, carbon. Yes. Oxygen, we'll go around it. We need 3 positions, apparently, like so. We need to hook that molecule up. So 1, 2, 3, 4, 5, 6 so far. Make sure you go to the outside parts first. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And lo and behold, this one's actually pretty similar. So you might say, well, you know, we just did this one. We did. But also notice that nitrate has a 1 minus charge, carbonate has a 2 minus charge. So it just depends. Just because they have different charges doesn't mean necessarily they're going to give you different structures or different types of looks to them, right? Which pair do you want to move in here? Obviously, we got the same problem, right? We only have 6 around carbon, so we take, well, I don't care, whichever ones you want. There you go. Okay.
Interruption, grade 12, last name starting with the letters H through M. We put it later for your pictures now.
Oh, you guys didn't remind me, by the way. Okay, 2 minus charge. You know, once again, you didn't. We'll talk about, you know, do I have to use dots or can you use lines there to represent the sharing? Sure, you can. It's fine. You'll see both. Mostly, you'll see the dots. So you might see something like. Oh, I guess I did that on the last one, didn't I? Okay, something like that there would be fine. Whatever. But you can use lines if you want. But remember, the lines are only used for bonds between different atoms, yes? So just keep that in mind. That's a 2 minus there. That's not very neat, is it? There you go. Okay? We're going to do one more real quick here because I'll show you. They don't have to just use this for polyatomic ions, so ions, things with charges. If it's got a charge, I would not do anything but, that's double negative. I would most certainly do this kind of thing, add up the valence electrons, etc. Okay, what we just did. If there's a charge, I would do this, absolutely. Even I would. I would not try to take any shortcuts. If it doesn't have a charge, okay, I'll give you another example here, SO2. Just SO2. If it doesn't have a charge, you may want to consider what we did yesterday. It might work out very nicely and evenly, and everything might just match up and you're done. Okay? And, you know, do we really need to go through 4 rules, or 5 actually, there's almost 5 steps there really, or actually almost 7. Do we really need to go through all 7 for some simple ones like NH3 and CH4? Probably not. Okay? If you want to, can you? Absolutely. Knock your socks off. Go right ahead. But do you have to? The answer is no. So you might say, well, SO2 doesn't have a charge, so let me try and draw this one. So I would say, well, you know, sulfur If I was doing it like we did last day, it would look like this, right? Oxygen looks like this. You might say, how do I know which one to start with? Well, I'd start with, they both have 6 valence electrons, yes. They both have a bonding capacity of 2, sulfur and oxygen. So, you know, which one should I put in the middle? Well, they want to be symmetrical, so we usually put S in the middle, and then the O is there. And then you'd say, oh, I can hook these 2 up here, and I can hook these 2 up here. And then we get to this stage here, and the question becomes, now what? So, we see this, and we see this, yes? But, I actually forget if it was your class or the other class. Can you hook those up? Are those on adjacent atoms to each other? Are they on an, is that electron right beside the other electron on the same atom? Remember? We talked about, like, for example, yesterday, carbon. Here's an oxygen. And here's an oxygen, right? Well, those are going to hook up, those are going to hook up. Can I hook up those 2? Are those on next to each other? No. Are these technically next to each other? Or do I have to? So do I have to go through S to get to O, basically? Yes, you do. Okay? They're not next to each other. Is this connected to right here? Is that electron right here? No. Is that electron right there? No. People want to connect those together. That is a no-no. Okay? You cannot connect those 2 together. That never happens. They're not on adjacent atoms. Okay? So no, you cannot. In fact, you cannot make rings, we call them, ring structures, triangles, squares, whatever, with those kinds of atoms. I'll tell you though, carbon's very good at rings. So if you had all carbons, yes, you can get away with that. Okay? But that's the only atom you can do rings with. Or you can do things like, this is organic chemistry next year. Okay? Rings. Yes. Very good at it. Carbon's very good at making long chains. Hydrocarbons. Gasoline. Okay? Stuff like that. Ethanol. All those terms. Propane. Very good at that. Okay? They can make rings. Okay? Stuff like that. But this one here, sulfurs and oxygens, cannot make rings. All right? So, this didn't work out quite like I had hoped with just putting up atoms and matching them up. So, how could I do this? Well, you most certainly are always most welcome to do counting up electrons, right? In this case, you got 18. All right? Now, this doesn't happen very often, so I'll quickly tell you. If you get SO2, that's kind of the ones you just kind of have to, I don't say you have to memorize it, but it doesn't hurt, because that way you know that it's not going to work out nicely, and you can just go, okay, this is the one that doesn't work out very nice. I should probably just do the electron thing, okay? So that will help you save some time. You don't have to memorize it, but it doesn't hurt, that's for sure. So SO2 is one of the tricky ones. So 6 and 12, 18. Which one do you want to put in the middle? Probably the sulfur. Right? There's only one of them. We're going to hook up, obviously, these molecules. So I'm going to use 1, 2, 3, 4 right off the start. The rule says we need to go to the outside atoms first. Okay, so there's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16. Now, have I used up all my electrons? I still have 2 more, right, that I can put somewhere. It says that if there's extra electrons and you made the outside ones filled up, which I have, oxygens both have 8, I've used 16, the 2, 17, 18 can go on the central atom. So I'd put them there, 18. Now I've used up all my electrons. The question then becomes, is this good? No. Sulfur needs more, yes? So how do I fix it? You pull a lone pair and put them in there, for example. And the structure you'll end up with is something like this one here. Okay? And if you did that for me, that's fine, because I can see that each one's got 8. You've used all the valence electrons. It's all good. Is the structure linear? And the answer is no. Okay. Once again, that'll take a little time, but technically that kind of thing is what you're looking for. Okay. How many things are around the central atom? Look, a bond right here, a double bond, sure, but a bond, another bond, and then a lone pair. So technically around that central atom there's 3 things. So I need to kind of spread out those 3 things. Okay? So that's what I'm doing here. Yeah. So you're saying that maybe this up here, this lone pair is not there? But there's only 2, yes? So if there's only 2, it's going to make a linear line straight across. But once again, remember, when you're doing those ones for homework, you can move, right? So where do you kind of start? If you only have 2 atoms, I don't want to do the homework for you. I don't want to give it away. But if you only got 2 atoms, let's call them X and Y, which one's going to be your central one? Pick one. Yeah? Does it really matter? I guess, if you want to, sure. Yeah, you can pick one. Pick the one that has the most bonding capacity or whatever, right? But if that fails, then it doesn't honestly matter. What I do know is I have to pick that, right? Then I got to start somewhere else. I got to fill up one of the 2 for the octet. So I'd go, okay, I'll start here. So I get that done. So fine, that's got 8. Do I have any extra electrons? If I do, I'd have to put them over here because I can't put them here because I already got 8. So let's say that. And let's say that. I get that, right? I don't know. And so now you're done. You used up all the electrons. But how are you going to arrange it so that they both have 8? Well, now you'd have to move one, right? So you take that pair and move it in there, for example. Now both would have 8, right? So that's kind of what you need to do with a few of those questions for homework. All right? That makes sense? And maybe that's all you have. Well, in that case, you got more work to do, right? Well, if that's all I have, I better start moving pairs in until that fills it. It's always got to have 8. How are you going to get the 8? You got to move pairs of electrons, yes? So just keep that in mind. Okay, good? Good question. Anybody else? Questions? Yes, no? So hopefully that's good enough. Hopefully you guys got a good cross-section there. Have those. There's only 4 questions for homework. Have those done for tomorrow.